you like access. You type a language like search, and then it gives you access to like the original books, like the original hadith books, the original thing, and it just pulls up the text for you. It's really good.
Is it a spin-off of Hadith.ai that they shut down?
Maybe, I don't know. Ansari chat is similar. Ansari chat is more of a regular chatbot. Usul is more research. No, just text. But it's like the original, like the original text from like 1,000 years ago, and they have them all indexed. You can search whatever, like the whatever hadith you want, whatever like stories, Sahaba, stuff like that. Gets you the original text of everything. Yes.
I was also thinking about the prayer times.
Yes, we can do stuff like that. Yes. Subhanallah. Alright, shall we get started? Bismillah ar-Rahman ar-Rahim. As-salatu was-salamu ala Sayyidina Muhammad wa ala alihi wa sahbihi wa sallim. We start by renewing our intention. Inshallah, we're here to learn something that is pleasing to Allah. It's ilm in some way. We're going to be talking about motion planning. Thank you all for coming. Jazakumullahu khairan. It's actually more than I expected, so I'm glad to hear there's some interest in the field. And we're going to start with sort of a very high overview of autonomous vehicles, inshallah. And we're going to very slowly dig deeper until we get to my favorite motion planning algorithms. Inshallah, if we have time, we're starting a little bit late. If we have time towards the end, we'll have a hands-on workshop where you build your own really cool motion planning algorithm. It's somewhat recent. It's only like 20 years old, which in the world of research is not that old. It's one of my favorite algorithms. It's used in the real world sometimes, and it's super cool. If we don't have time, I'll just share the link to the Jupyter notebook, and everyone can do that on their own. So Bismillah ar-Rahman ar-Rahim, we start. So a little bit about me, just a quick intro. My name is Mahmood. Nice to meet you, everyone. I've been in the self-driving car world for a little bit of time now. Since May 2018, I started with Uber ATG, Advanced Technologies Group. So this was part of Uber. That's this picture there. That was at the time, it was one of the big self-driving car companies along with Waymo. It has since been acquired by Aurora. So I joined there as an intern on triage, working on developing tooling for triage. Then I started working on motion planning. And subhanAllah, since then, I've been working on a lot of motion planning. So after that, went back to the University of Toronto for my last year of university. Joined Toronto, which is our self-driving car club. That's this one right there. So that's our self-driving car. We won first place, alhamdulillah, in the self-driving car competition. It was basically a self-driving car club that was like funded by a bunch of super popular companies that you would have heard of. Intel, General Motors gave us this Chevy Bolt, MATLAB, a bunch of other companies. Graduated, went to May Mobility. So this is me next to our May Mobility car in downtown Ann Arbor. So May Mobility is in the south of Ann Arbor. I did more motion planning stuff there. The MPDM framework is how they do motion planning. So that was my experience with them. So was there for about 2 years. Then I joined Argo AI. So Argo's Ford's. It was a Ford and Volkswagen joint venture. So joined them, worked on their self-driving car as a motion planning engineer. Let me finish the slide, and then I'll take questions every once in a while. Is that okay? Okay. Motional. So Argo AI eventually got absorbed into Ford. I joined Ford for a very small amount of time. It was called Argo Blue L3 at the time, renamed to Latitude, if anyone's heard of that. Joined Motional for about 1.5 years. That's Hyundai's self-driving car. That's this one, using the Ioniq 5s, also motion planning. And then right now, about less than 1 year ago, joined Woven by Toyota. So this is me on Friday or Thursday with our self-driving car. It's a Lexus, and I've been working on their ADAS system. So I'm a senior software engineer there working on motion planning. Hiba, question?
In 2020,
Mm.
like city-wise, did shutdown affect your work in any way?
Oh yeah. It was interesting. Alhamdulillah, most of the work ends up being online, but yeah, it was definitely a big effect because a lot of testing used to happen in person. After 2020, a lot of testing became sort of simulation based, and a lot of work happened from home. But alhamdulillah, it wasn't too bad. I mean, work kept going.
Are we back away from simulation into in-person?
No, not quite. Simulation's still very important, but oh boy. But yeah, I mean, in person is happening a lot more than it used to in 2020 for sure. All right.
MashaAllah, how did you do this?
Yeah, this is Gamma AI. It's a new tool. I've never used it before. Hopefully, it doesn't fail me this time. Alhamdulillah, so far so good. Gamma, yeah, it's like an AI slideshow maker. It's good. Uh, okay, so we'll start at the top. We'll start with robotics. So robotics is the sort of high level, over encompassing general category. These are robots, manufacturing robots that you've seen before. Like in my first role at May Mobility, my title was robotics engineer. So we're all within the general field of robotics. So what's robotics? It's sort of the idea of making these intelligent machines to automate tasks. So in the case of autonomous driving, we're automating sort of the idea of driving. Maybe for like a vacuum cleaner that Siraj is working on, that's going to be automating vacuum cleaning. In this case, it's automating manufacturing. The whole idea of robotics is automation in the physical world. And yeah, in this case, we're going to be focusing on autonomous vehicles, inshallah. What is autonomous driving? Autonomous driving is sort of this idea of having a car drive itself, and the very high level overview of how that's supposed to work is we start by sensing the world. So we start with sensors, and we're going to dig deep into these, into what each of these steps means, how it works. But the high level idea is sort of this sensing step. So you'll have in this toy picture, you'll have the LiDAR, the video cameras, you have odometry sensors, you have radar sensors in front of this toy car. So you'll have all of these kinds of different sensors stuck to a car. All of these sense the real environment. That's step one, always. And if any of these sort of fails, they should have redundant fail-safes. They should have plans for what the car should do if it stops seeing the world. And then the next step is you have to understand all this data. Each one of these LiDAR scans is like megabytes and gigabytes of data. This is a ton of data. Each picture, I mean, think of how fast your phone runs out of space, right? It's a lot of data. It's a lot of memory that that you need to understand, you need to process, you need to combine all the sensor data, and you need to act, and you need to make a plan for how to react to the world around you, how to get to your destination. And that's sort of where I live a little bit more. This is more hardware engineering. This is more control systems. So the last step is executing actions. That's more of the control system world where given a set of instructions, like the car says, hey, I want to go on this specific path with this speed and this acceleration, how much brake should I press? How much acceleration should I press? That's where the control system part lies. And this is very complicated because different cars will have different responses to how much pedal you press, how much brake you press. And so a lot of work goes into this step as well. Please.
Convolution layer because it is deep learning?
Yes. So the way I mean, this picture is just sort of one of the steps here, but yes, the camera data, in order to process it, as far as I know, almost always, maybe literally always, it has to go through a convolutional layer first and then processed by deep learning, exactly, for the camera data. LiDAR has other, I think NERFs is what they use these days. Radar, I don't even know what they use. Question?
The numbers, the 3x3 square, the
Oh,
7x7.
yeah, I wouldn't read too much about this. It's just a random picture. This is the size of each matrix, or tensor, actually. Yeah, this.
This is at the top of the car. This is the controller.
Yes, so the controller is more a piece of software. It's usually a separate computer. It's actually usually two separate computers in each car. So each car will generally have multiple computers specifically for controls that are completely separate from everything else. They follow a very high safety standard called ASIL-D. It's like this is the most safety critical part, because imagine there's like a cat or a person or a child jumps in front of the car. You really cannot afford to have the controller have a bug or an error in it. So when the controller says slam on the brakes, that part is the most crucial. So it has multiple computers redundant to each other, 2 to 3 at least. It's connected via multiple wires as well, right? So it's not just one wire going to the brakes, one wire going to the accelerator. It's actually redundant wiring. So it's a computer, It's wiring. It's multiple computers, and it's connected to sort of the car systems.
Is the controller running at 100 hertz?
Usually, yes, very high speeds. 100 hertz means once every 10 milliseconds, 100 times a second. Yes, 100 hertz. I've seen 200 hertz as well. Nothing less than 100 though. So this is very fast. The blink of an eye is around 100 milliseconds. So this is 10 times faster. Like the controller is one of the most sort of.
But some car like Tesla, they don't have this in the car.
This is more for the sensing bit. So that's this sort of LiDAR part. A lot of cars, our cars included, have sort of stopped using this, sort of relying more on the video cameras. That's okay. That part is just one of the sensing modalities. Different companies. It's actually a big fight among companies for like whether or not you want to use LiDAR or not. So this is a laser scanner, basically. Your iPad actually has a very cheap, simple version of this. Face ID works like this as well.
Is that time of flight camera, TOF?
I don't know. What is time of flight?
Sends out pulse of light, and then each pixel it measures how long it took for that pixel, that light to reflect.
That's how LiDAR works, yes.
Okay.
Yes, yeah.
This is like, it's a pixel array.
They don't call it pixels, they call it point clouds. Yes, yeah, so
Like the sensor is a pixel.
yes, yes.
Are they
Like an
expensive?
array. It's an array.
Are they
TOF
expensive?
cameras.
Are they expensive?
Phones have had them for a while.
Yeah, I mean, these are very expensive.
Because one of the biggest reasons that people don't want to use LiDAR is because it's cost.
They've gotten cheaper, but yeah, they used to be $60,000 to $100,000 a pop for these. We call them KFC chicken buckets. We've called these KFC chicken buckets for as long as I know, especially in this picture. I mean, it really looks like one. Yeah, it used to. Nowadays, they're much cheaper. I think they're on the order of $10,000, even less. No, I think even less. I think they've gotten a lot cheaper. All right. So let's start with some terminology. There was supposed to be a picture here. That's okay. So this is a very common piece of terminology that you'll see all across sort of the literature. You'll see people talking about this all the time. It's very important to know. I'll go through it a little bit high level here, and then we'll dig a little bit deeper over the next two slides. So it's the levels of automation of a car. Or any autonomous system, but we can focus on cars for now. So it goes from 0 to 5. 0 being no automation at all. That's like you driving your 1967 Volkswagen Beetle. 0 automation. Level 1 is like your 2003 Camry with the cruise control that just sets the speed. So this is sort of the one feature that controls the car in one dimension, right? So it'll control acceleration. The next level, level 2, this is where sort of most cars are today, and probably for the foreseeable future, for the next, I would say 5 years, we're probably going to stay in this world. Even the latest Tesla is here. This is where the car controls itself. It sort of drives itself, but you are the person in control. You're the person driving the car, right? So when you turn on your lane departure warning on your like 2019 Corolla, and it's sort of centering you within the lane roughly, and it's stuck, and it's like maintaining a certain speed. A lot of cars will have radar as well, so it'll stop before the car in front of you. Going all the way up to like the latest Tesla full self-driving, in quotation marks, where the car fully drives itself, stop signs, traffic lights, safety maneuvers, parking lots, everything. But the key thing is you're in control. Left turn, everything. I mean, Sheikh Ibrahim has one of those Teslas. I had a chance to drive in it. Amazing. But it's still level 2 because technically you're in control. Level 3 is one step later. A lot of people have actually debated if this is a real level or not. It's where the car is in control, but you're sitting there. So this is the idea of reading a book, right? So you don't need to pay attention to the road. You can sort of read a book. You can browse your phone. Very few cars have this. As far as I know, one car has it, which is one of the Mercedes S-classes, and only on certain roads. I think Super Cruise has ideas of adding this as well in their GM systems. in the future, but I don't think legally speaking anyone other than Mercedes has this. So the car is in control. The car does not need you there. But if the car gets confused about something 10 seconds into the future, the car will say, hey, help me out. So it'll give you a chime, it'll wake you up if you're sort of not paying attention, and it'll ask for you to take over, right? So you're there, you're in the car. The car needs you to reach its destination, but it's not quite, you're not required to pay attention. You're not required to be the safety system for the car. Next up was level 4. This is the Waymos of the world, the robo-taxis. This is May Mobility. This is what Cruise used to be. This is sort of where a lot of the work was back in 2018, 2019, 2020, even up to 2022, 2023. Sort of a little bit dying down with Waymo sort of being crowned king. In China, this work is still ongoing and they're going pretty fast. Level 5 is sort of another very controversial level. It's sort of this fictional idea of full autonomy. This is like driving in Cairo or New Delhi or Karachi, right? Like this is like the car can do anything, right? This is the idea, or Dearborn. This is the idea of a car that can like really fully navigate in whatever situation you throw it in at the level of a human. It's sort of controversial because if you've heard of the term artificial general intelligence, it sort of gives a little bit of the same vibes where like, is it really realistic? Is it really a thing? So let's dig into these a little bit deeper. We went into good depth. I guess we'll recap real quick. Level 0 to 2, this is sort of the humans in control, right? So 0, that's this bus with no buttons to drive the car at all. Level 1, that's the cruise control. That's the set speed, maybe even set speed with like slowing down for the thing in front of you. Level 2, that's anything from lane keep to Tesla full self-driving. A lot of the Chinese cars these days, they would blow your mind with how good they are, even better than Tesla or just as good. Level 2, you're in control. If something happens, if you hit someone crossing the street, you're in trouble. Tesla's not in trouble. Legally speaking, when you turn on the Tesla system, it's not taking control of the car. If you get in an accident, if you kill someone, if something, la samahallah, happens, you're the one in trouble. So you need to be paying attention 24/7. If you do have one of these cars, please pay attention 24/7. They're not as good as you think. All right, and then level 3 to 5, that's sort of this idea that the car is in control. So level 3, the car is sometimes in control. Level 4, you don't need to be in the car. Level 5, full automation. The car is, I guess, can drive wherever it wants.
Which car they are for Tesla?
Yeah, so level 3, as far as I know, just Mercedes. No one else. And even then, that Mercedes car, only on very specific highways that they've approved. Some highways in California, I know for sure, some highways in Germany. I don't even know if there are that many highways. It's very early days. Not a lot of cars are here. Level 3 is very rare.
Is Latitude working on that?
I think Latitude is working on that. Yeah, I think you guys at Cruise are probably going to be working on something like that. The problem is the liability, right? If the car kills someone, if the car hits someone, while it's in this level 3 autonomy mode, the company's in trouble. Like Mercedes right now, with the system they have, they take liability. If Mercedes car on the highway, while the level 3 system is on, engaged, gets in a car accident, Mercedes can be taken to court. This is revolutionary. I mean, no one has this, right? What?
Is this why people are not like?
That is exactly it. The reason, like, Tesla is better than Mercedes. Hands down, for sure. Not even close, actually. Tesla is a much better autonomy system. The problem is they don't want to take that liability. They want to stay at level 2. They want to be in a situation where you're in trouble, not them. No, Cruise is level 4. So level 4, there's no one in the driver's seat. There may be a driver's seat with a steering wheel. There may not be. So if you guys have tried a Waymo or a Cruise, this is what they're doing. There is no driver. With level 3, there must be a driver. Because at any point, the car can say, hey, listen, man, 30 seconds into the future, there's some construction zone or something. And I don't know how to handle that, so please take it from me. And there'll be some sort of agreed upon time that you accept for like, oh, if the car needs my attention within this many seconds, 10 seconds, 30 seconds, 40 seconds, it's usually in that range, I'll come back, I'll drive the car. It'll pull over, exactly. So if you're sleeping, the car should be able to just pull over to the side, turn on the blinkers, and just stop there, maybe in the middle of the road, but safely. Level 4, there's no one there. There's no one behind the driver's seat. So in the latest Waymos, they don't even have driver's seats. In the older Waymos, they do have driver's seats, but there's no one there, right? Even Tesla, actually, they do have a level 4 system. So Tesla technically has a level 3 system. So if you guys have seen the Tesla Robotaxis, there's a person sitting on the right side. There's no one sitting on the left side. That's, I think, technically level 3, maybe level 4. It's sort of in that edge. I don't think it's available for the public, although it might be actually. In Austin, Texas, it might be. So this is sort of the Robotaxi idea, right? This is, every company I've worked at has been level 4 until Waymo. Until Woven by Toyota. So I've worked at Uber ATG, that was level 4, all the way back in 2018. Worked at May Mobility, worked at Toronto, at the University of Toronto. Argo AI and Motional, they're all level 4. Level 5 is basically science fiction. There's really not much to say about it. It's very far into the future. Like this whole concept of unlimited operational domain, all weather conditions, it's really, I think SAE, the organization that made this that made these levels, just put this there just to have something to aspire to, or just to have completeness with their leveling.
So what's the difference between 5 and 4?
5 is like the car can drive anywhere. It's sort of like a professional driver, you know? If you get like the best driver, where can they drive a car? To be fair, a human is sort of at level 5, right? A human can drive in rain and snow in Karachi, and like a human can drive in very different conditions, very difficult conditions.
Do we have cars in level 4?
Level 4, yes.
Level 5?
No, not at all. Not really anytime soon. 20 years, I don't think we're gonna get level 5. Maybe 30, 40 years. Inshallah, it's hard to tell.
Question.
Yes.
For the level 4 designers or researchers, when a 16-year-old child is learning to drive in Michigan,
Yes.
it's very local to tell them the deers could, when they're on the side.
Very
deer
true.
could pop up,
Yes.
or a snowstorm could hit.
Very
Is it-
true.
What kind of parameters are they looking at that is not Michigan, not deer, not hailstorm?
Excellent question. So with level 4, we actually have, the really nice thing is this whole geo-fenced operations, right? So you can drive in certain areas, right? So you'll have a Michigan car, and you can have sort of a system that's tested for Ann Arbor specifically. So May Mobility, they test in Ann Arbor. And then you'll have like a San Francisco tested system. So you can make sure within that area, whatever things that are common, deer, we have the hanging traffic lights in Michigan. I don't know if you guys know this. These are very difficult for an autonomous system. I know even Waymo had trouble with this. The wind, exactly. So you can test within an area before enabling it, right? That's the whole geolocation, the geo-fenced operations area. So you'll test a certain area. It'll be like, okay, we can handle this, the deer. If we can't handle Karachi, we won't enable the car in Karachi, right? So that's why the level 5 thing is a little bit, I don't know why I'm picking on Karachi. I just heard like nightmares about driving in Karachi, I guess.
What are the parameters in Austin? What are the parameters in San Francisco that we don't have?
I don't know specifically. I know their roads are a lot wider. Yeah, it's just generally different. Even driver behavior is different. Some areas people would be more aggressive. Yeah, snow versus sun. Some places might have a little bit more heavy rain. Even just specific, like, for example, we tested in Las Vegas. They have these like very specific, really big hotel lobbies or like hotel pull-in areas, right? So that requires, the circle drive for dropping off people and picking up people. Like those are very difficult sort of situations for a car. So you have to make sure you test in that area before you enable it. So that's the whole level 4 area, level 4 kind of idea. Level 5, no testing, just Bismillah, run it. It should work. Japan, exactly. You're driving on the opposite side. So with level 4, you make sure whatever system you're testing sort of works in that general area or that specific road. So some companies like May Mobility will actually test on the specific road back and forth until they make sure they get it right, and then they'll take the driver out.
Where's the parallel parking difficulty in these levels?
It depends. It's not really about specific maneuvers like parallel parking. A parallel parking system can be level 4 if there's no one in the car. Can be level 3 if the car is like in control and takes liability. Can be level 2 if you're taking liability and you have to stop it. So a lot of systems can be like, it's not how hard the problem is, it's who's in control, right? So the whole like, is the car in control? Or are you in control? Good question so far. Anyone else? All right, bismillah. All right, so let's get into the nitty gritties, the architecture, the actual how this stuff works. So super high level, sensing, we've already talked about this. Cameras, LiDAR, radar, GPS is a sensing modality. IMU, that's the inertial measurement unit. That's what's measuring acceleration, jerk. This is just data coming in from sensors to understand the world. Next up, we have perception. Perception is the idea of checking or understanding this data. This is a ton of data. Cameras, huge. LiDAR, huge. Radar, really big. GPS, not so big, but you do need to process it. IMU, it is a lot of data because it's coming in very quickly. Perception is the idea of taking each one of these separately, understanding it, then combining it to understand localization, is understand where am I, where's the car, down to the millimeter for a lot of systems, right? Where exactly am I on this road? Where am I, which city, which road, which centimeter on which road, right? Compared to the physical environment around me, compared to the lane lines. The other thing is object detection, right? What are these things around me? The thing in front of me, that's a car. How big is it? How fast is it going? Okay, is the car turning left or right? Does it have its blinkers on, right? That's very important. I mean, a lot of things that we don't even think about, like, does the car have its wheels turned to the left? Those are things people pay attention to. Faris?
Are they getting less dependent as they get better? Like, do they care about lane lines as much right now?
Depends on the system. So if the system is a level 2 system, oftentimes it really depends on the lane lines because other people around you depend on you depending on the lane lines, right? If the lane lines don't really exist, does that mean the car won't work? Depends on the system, right? More advanced systems? No, not necessarily. So if you get in a Tesla, an FSD Tesla, if the lane lines are not there, it'll draw its own lane lines. Like, it'll imagine them. And it'll be pretty good with that.
Can it see the tarmac from the grass and
Yes.
the ditch?
Yes, exactly. So that's called drivable area. That's a very important thing as well. Exactly. So the concept of drivable area is the concept of like, what can I drive on? What can I not drive on? So that comes from your LiDARs, that comes from your camera. And again, the idea of accepting all of those inputs, combining them, processing them, and then understanding the world around you, and then understanding what objects are. Tracking is the idea of understanding this second I saw this object. It's like 2 meters long, 1 meter wide. The next second, there's another 2 meter long, 1 meter wide red object. Is it the same as the one from last time? This turns out very difficult problem to solve. It's the idea of sort of this temporal consistency over time. Next up, prediction. This is the idea of sort of looking at the history of these objects, looking at what they look like, looking at if they have their blinkers on, looking for people where is the pedestrian sort of pointing their head, looking at how fast they're moving, and understanding where they're going to go. Over the next 5 seconds, 10 seconds, where are they going to go? This is actually a piece that's sort of disappearing a little bit with time. It's sort of being absorbed into perception and planning. We'll talk a little bit more about that in the future, but historically this has been a very core part. It's a large team that includes dozens of people in many companies. Next up is planning. Planning is the topic of this talk. This is sort of where we'll spend most of our time today, inshallah. This is what I do, motion planning. It's the idea of, hey, I'm trying to get somewhere. I'm trying to get to Kroger. What do I do? How much, if I am sort of on Palmer at this very specific second, there's someone crossing the street and I'm trying to get to Kroger. How much brake should I press at this specific moment in time? How much accelerator pedal should I press? How much steering wheel input do I make? And then the last thing is control. Control is like, so I guess I sort of combine the two. Planning is more planning a path. Control is more like executing the path. So the planning system will say, hey, there's a person crossing, slam on the brakes. Controller will say, apply 6 volts to the brake system so that we slam on the brakes, right? Control is very vehicle dependent. That's one of the difficult things with it. Every single car, every different car will have different control parameters. The control system will depend on the physical system of the car, how well it responds, how heavy it is. It's a whole wide world.
Which of these things makes difference between 2, 3, 4, 5?
All of them, really. All of them and none of them, to be honest. So, again, with 2, 3, 4, 5, you're sort of asking the question of who is in control of the car. One exact same system can be 2, 3, or 4, depending on, say, what the lawyers decide, right? Or depending on how well it's been tuned, right? So the level 2 systems will actually have a very similar stack to this, and the level 4 systems will also have a similar stack, and the level 3 likewise. Level 1 won't be like this. Level 1 tends to be a little bit simpler. Oftentimes, you can actually just not have any perception or sensing for level 1, or you can have a very simple sensing module, no prediction, very simple planning, mostly controls. So that's level 1. Level 0, obviously, you won't have any of this. Level 5, you also probably wouldn't have any of this. You would probably combine them all into one big artificial neural network, and I don't know.
Isn't that what Tesla is doing?
Sort of. Kind of. Tesla actually does have these separate systems. It's all hard to tell exactly what they're doing, but you sort of talk to people in the industry. Word on the street is they do have these separate blocks. The difference is they're connected to each other through like feedback loops. So the neural networks are connected to each other. So as you're training, you get sort of feedback all the way back, propagating through your neural network back to your perception layer, through the whole thing. So it's the idea of end-to-end, but they still do have discretized chunks. Other companies, Wave, I believe, is a British company. They're known for not doing this like separate blocks. They actually just have one big giant block. I believe Wabi as well in Toronto are doing something like that. And I'm sure even within Tesla and these companies, they probably have researchers working on sort of next generation systems that combine
I
everything.
remember seeing a video like from way back in the day of VHS.
Yes.
In the 80s, they had you probably have seen this, right? They had some sort of neural net.
Mm.
I don't know if they took the 2-dimensional video image of the road as
Uh-huh.
a control road,
In-
right? Like,
In the 80s?
90s maybe?
Mashallah, I didn't know about this,
Okay,
yeah.
But it was very simple. It
Yeah.
wasn't driving outside.
Yeah, but it would like stay within the lines.
Yes.
Nice.
So it was, I'll try to dig up the video.
I would be interested.
And I forgot what the inputs were. I think it probably wasn't a bitmap image of the road, or maybe it was very simple file.
Mm.
And then it gave, a neural network.
Right, a neural network.
That controlled.
Wow.
I mean, very simple, right?
They were around, but
Like 2001 or something.
convolutional neural nets were not around.
Yeah, I mean, obviously
Oh,
not
sorry.
that many parameters, wasn't that big. It was probably.
But it worked.
Yeah.
Mashallah.
It very slowly drove the car through a controlled little track.
That's amazing. If you can share it, that would be amazing. Yeah, that's very early. 2007 is when things.
It was all together, I believe.
Maybe.
So I don't know if you're gonna go into each of these.
We will, but
Okay.
ask your question.
Okay. I'm very curious. The control block.
Mm-hmm.
Since there is so many variable things, is there sort of like, different vehicles? Each vehicle even like has different modules.
Yes.
Is there sort of like a standard protocol that each of them use to sort of like do the mappings between the planning and the controls?
The planning and the controls?
Or whatever.
So, yeah, it
whatever
depends.
the-
Planning and the controls, no. Every company will have their own custom thing. The thing planning is spitting out is often a trajectory. So we'll talk about what a trajectory is. It's just a set of points. The control system has to follow that. So that's very company dependent. So a company that might produce 10, 20 different types of cars, they'll probably have one type of trajectory that they define. And so all their separate controllers for each car will be unified, sort of according to that company standard. On the output side, there are more sort of industry-wide standards. So that's the CAN bus. That's the these days IP something.
Yeah, these are like communication dependent.
Yes.
No?
Yeah.
So
Yeah.
I'm talking about like controller dependent, like telling a this system, the voltage for it is different than another system. So telling it push out 6 volts like you mentioned,
Yeah.
versus another system telling it to push out because it's the same protocol.
Yes.
You're gonna
Yes.
push out 12 volts.
Yeah, that's going to be company specific. That's going to be every company will have that kind of system. At Woven, we do
But
have.
then
There's no standard as far as I know. No.
AutoSAR is not used over here.
AutoSAR is more of a safety standard. So AutoSAR is the idea of the code you write has to meet a certain specification of quality. So every control system has to pass the AutoSAR certification, but there's no specific sort of definition of what the exact parameters need to look like, how it's structured. Every company has freedom to do that.
Yeah, so the idea of AutoSAR was that multiple vendors can have like the same amount of code. Like it's like making the code more plug and play. Like that was my understanding of AutoSAR. Like
I might be mistaken then.
yeah, because what we're talking is more like for ASIL safety.
Yeah,
like,
ASIL D and
yeah,
ASIL
you
B.
have to maintain like all those standards. AutoSAR
Maybe I'm thinking of AutoSAR C++
yeah.
standard, but
Yeah, yes, it's making sure the software is
plug and play.
Yeah, different.
Within the control
Yeah.
interface as well?
Yeah.
Okay, I didn't know about that. Yeah, jazakallah khair.
Question.
Yes.
Forget Chinese electric cars.
Yes.
Within this country,
Yes.
there's Tesla, but then there's also the GM and the Ford.
Yes.
By Chrysler.
Yeah.
How much is cooperation and how much is?
Yeah, that's a good question. I'm not sure. You might know a little bit better. Sorry, what's your name? Samir. Mahmood, nice to meet you. I don't know. I think it's mostly competition, but Samir.
Yeah, I work in motor controls. So
Yeah.
Like that's how I know a little bit about control side of things.
Yeah.
But I don't think
Do
so.
you
They
work
should.
for one of the companies?
Yeah, I was working for Ford before and worked for Mercedes-Benz. Now I'm with Hyundai.
MashaAllah.
So yeah, so I don't think that they share. They made sometimes like for electric cars I can tell like they had this organization where they were developing a common code and then after a while they decided to branch off.
Yeah, I think it's mostly competition.
Yeah, mostly, yeah.
I think it's mostly
Yeah.
competition.
But then, when does it become generic? Like in medicine, you can invent something, and after 20 years, it's not patented.
So you have similar over here, like patents over there. Like if it's a patent, like either you have to buy. So what I've seen, like sometimes, like Ford has taken patents from Toyota, and they pay Toyota the royalty.
Yes.
So that's one way of doing, like I would say, like working together. Or sometimes companies have these partnerships, like Ford had with Volkswagen for Argo AI, so they were working together. But I don't think so. Like they share it commonly. Like, it's not open source.
No standards right now.
Yeah.
All right, let's keep going. So let's dig a little bit deeper. Perception. So perception is the idea of, again, we talked about this, sort of understanding the world from your sensor data. We skipped sensing. We sort of talked about this. I'll go through this quickly because we are sort of only 45 minutes left. So the main sort of parts, again, we talked about this object detection, understanding, hey, like there's something there, there's something there, there's something there. Semantic segmentation is sort of the idea of like every pixel, every point in your world, what is it? Is it a tree? Is it a ground? Is it another car? Is it a person? Sort of what exactly is going on with every part of the world. Localization is the idea of understanding where you are. There's whole books written on this. This is very critical. It used to be very, very critical in the world of LiDAR because you needed that millimeter accuracy. These days it's a little bit more loosey-goosey, but still within centimeters or several millimeters instead of single millimeters. And then tracking is this whole over time, right? Let's go quick.
What is the tolerance for from 1 millimeter to more?
I think part of it is the LiDAR systems required sort of the high degree of localization. They also enabled it. So LiDAR systems are much more sort of accurate. As you depend more on camera data, you don't need that sort of distance measurement. And you also it's harder to get with a camera. You really need sort of more your relationship, your position with respect to the world around you. Another thing is with machine learning systems, they're a little bit more robust to noise. Tesla's only use cameras, yes. Other companies are now following suit, but Waymo and others are actually pretty strictly LiDAR based. So it's, although even Waymo has, like if you remove the LiDAR from a Waymo, it actually drives really well with just the camera systems, but they wouldn't tell you that. They would actually prefer to keep that LiDAR. High level ideas of how prediction works. In the ancient days, used to be physics-based systems. So you sort of see a person walking at a certain speed, you just assume they'll maintain their speed. You see a car decelerating, you can have a constant acceleration model. To be completely honest with you, a lot of systems are still based on this like physics modeling idea, right? Even when I worked at May Mobility, our prediction system was entirely physics-based. You can go really far with this, really far, because the idea of energy, right? When you have a car going at a certain speed, it's hard for it to change its state very much. So you can sort of maintain that constant acceleration assumption for a few seconds, gets you pretty far. Later on, sort of this intent-based reasoning came on. This is, if you guys know Lex Friedman, the podcaster, this was something I don't. He went off the deep end now, but he used to talk about this a lot. This was actually his PhD work. It's the idea of predicting where people will go. So going from point A to point B, you see a person sort of walking in this direction. You see a door over there. You can sort of infer that, hey, this person's going to this door. A lot of machine learning systems will actually use this as well. And it's very powerful because on roads, if you see a person, like a car driving left at an intersection, you can pretty clearly tell they're either going to this lane or this lane, right? You can sort of limit exactly where they're going to end up just based on their current position and sort of the direction they're traveling. So this is a lot of where sort of systems were in the like past 5 years, I would say. More recently, learning-based approaches combined with intent-based systems as well, and even combined with physics-based systems. This is sort of more of a, it's an innovation that uses the past two. So this is just using a neural network trained on 1 billion cars and sort of seeing, hey, when cars do this thing, here's how their position evolves over time. So I know what this car is going to do. Works really well. Faris? Yes. The learning-based approaches is what they would use for human beings. Palantir is not really for predicting physical locations of people at like in physical space based on camera data. It's more for predicting much more nefarious things and predicting who has a different opinion than the president. So it's much more of a different space. I don't think humans will use Palantir. A company that is very almost as evil as Palantir that does this actually very specific thing and does sell that module is Mobileye, also based in Israel. It's owned by Intel, and they do a lot of prediction systems. They're really good at it. So they do them for humans, they do them for cars as well, they do them for targets. So it's a company that a lot of car companies actually use, and a lot of weapons companies also use. Terrible company, but one of the larger ones, Mobileye. So yeah, they do prediction. Sorry?
What does Mobileye predict?
A lot of things. So they do driving systems as well, but they also do prediction systems for everything. People, cars.
So the physics and the intent mode, they don't use neural network.
Yes. Technically, historically, no, they don't use a neural network. For physics, I would say that's still the case. Intent-based, these days, it's all neural network. Figuring out sort of the intent of a user is all going to be based on neural network. But historically, no, they wouldn't. Learning-based approaches sort of encompass these two. So even a lot of learning modules will have a physics module at the end of it to make sure the thing I'm predicting is physically possible, right? So I don't, like if the neural network says, oh, the car is going to teleport like 20 meters to the right. Like that's physically impossible. It'll be fixed by the physics-based model. So this is a thing that sort of encompasses these two.
So they use at the same time three of them
Yes,
in the car.
yes. I would say that's a good way to put it. Depends on the system. There's a lot of variability here. Some companies actually wouldn't do any intent-based or physics-based modeling. They'll just have a learning-based approach and just one neural network. They don't even check it, and it works well for them. Different approaches.
Would things like mirrors really confuse these systems?
Yes, I've seen trouble with mirrors before. Mirrors tend to be problematic for older generation systems. With a lot of training data, you tend to sort of get better at understanding the idea of a mirror, the idea of a reflection. With LiDARs, you tend to do a little bit better. Although with LiDAR, you have the problem of retro reflectors, signs that are too shiny, metallic objects. They can cause issues.
So they have their own mirrors of some.
Yes.
The opposite of mirror night vision.
No, not quite. It's sort of mirrors tend to be sort of problematic for older systems. I think more modern systems they tend to do well with mirrors.
Can these cars drive in dark?
With LiDAR, yes. With camera, depends on the specific camera used. But generally, yes, they'll be able to with because oftentimes cameras will have really good HDR support, right? So they'll be able to drive it in the dark. All right, let's move on. Planning and control. So we've talked about this a lot. Don't want to sort of re-mention too much, but high-level planning, what the car should do, the path it should follow, how it should maneuver through physical space, how fast, how much acceleration, deceleration. Control is sort of just executing that command, executing that plan. Inputs to the planner. So again, now we're digging a little bit deeper into planning. What inputs do you need? You need high level, these four, really there's more, but these are sort of the high level idea. You need a map. You always need a map. How detailed the map is, that's going to be different from company to company, from approach to approach. Historically, like most maps, Waymo used to use this, millimeter accuracy. So they would go around mapping the world down to the millimeter, super accurate maps with LiDAR point clouds. These days, a lot of systems, they'll just rely on like a very high level Google map thing, not even lanes. I'd say for us at Woven, we use lanes. So our maps just have the lanes, nothing more. Historically, I've seen everything in between. Perception data. This is not the sensor output. The sensor output has been processed by perception. This is the actual detected objects. So the perception data that I'm consuming in planning will be stuff like, there's a car there, it's going 10 meters per second, and it's decelerating at a certain rate. It's red, it has its blinkers on, right? That's perception data. It's been pre-computed. It's in many ways human readable. Another thing that's a very important input to planning is the output of prediction. So we've talked about this, right? The prediction of over the next 5 seconds, at every single millisecond, where is this person going to be? This person crossing the street. Which path are they going to take to cross the street? This car making a left turn. How is it going to make that left turn at every single second along the way? And then last but not least, mission goals. What are you trying to do? Where are we trying to go? You're trying to go to Kroger. You're on Palmer. Kroger is your mission goal. You'll have a high-level route. This is part of sort of the planning thing, the planning system. You'll have sort of desired lanes that you're trying to go to. Oftentimes, the planning stack is just going to be, the goal, is just going to be stay in your lane, right? So when you're in your sort of Honda or something, you turn on the cruise control, the car is just trying to stay in its lane. That's its goal, right? And then it'll have a target speed, right? That's the speed that you set, the set speed. Maybe arrival time or something like that, right? So this is planning, right? This is not controls, this is just planning. Typically, this is sort of a mildly important point. You're running around 10 to 20 hertz. That's the goal. I've seen as low as 5. So this is basically, you're replanning every call it 200 milliseconds down to like 50 milliseconds. For context, blink of an eye, I think around 100, 150 milliseconds. So around how long it takes to blink your eyes, how often you're planning, right? How long it takes for the motion planning system to run, accept these inputs, plan a path, and spit it out to the controller. Yes, question?
Can you say more about the uncertainty estimates and multimodal predictions?
Yeah, so this is here, right? So this is the idea that like any prediction of the future is wrong with some probability, right? Even the world's best prediction system, because even I, as a person crossing the street, I don't exactly know. I might change my mind and go back, right? So this is just sort of the idea of based on our data, based on our historical performance of the system, for that specific person, for that specific car, what are the odds that it does the thing that we're gonna do, that we think it's gonna do? Is it likely? Is it unlikely? Is it gonna be, sometimes you'll have like covariances, right? So how likely are you to sort of deviate from that prediction? So very important for the planning system to handle that and understand it. Multimodal predictions, that's just the idea that like you can have a car at an intersection where it's one of those like single lane intersections. It might turn right, it might go straight, it might take a left, right? The possibility, like it's in one of those lanes where it has all the options.
There's not much to predict.
It will have a multimodal prediction, right? As soon as the light turns green, let's say, is the car gonna take a right, straight, or left? Sometimes it's impossible to tell. At a stop sign, often that's the case as well, especially if it's a BMW driver who doesn't turn on their blinkers, right?
Yes.
So if it's a BMW, you really need those multimodal predictions to like have all the possibilities. So if I'm coming straight, or if I'm taking a left turn, for example, I might want to consider the possibility that the BMW is going to take a left turn, even though they don't have their blinker on, right? So
Just about any car in Dearborn.
or Dearborn, yes, Dearborn or BMW, I think is what would.
I mean, even at the red light, you will have predictions very low with very low probability.
Yes.
But this guy's gonna run the red light.
Exactly, 100%. It's always possible. So the prediction stack needs to output these possibilities, right? So that's the whole multimodal. Multimodal means multiple possibilities in this context. The outputs of planning. This is a very cool picture I saw. This is sort of what the output of planning looks like. So it's a specific path in two-dimensional space that tells the car, the control stack, what I want to do over the next 4, 5, 6, 7, 8 seconds, right? So it's a path in physical space, so that's the spatial path, and it has a speed profile attached to it. So if, let's say, I want to go really quick to pass this guy, at every point along this path, the planning stack needs to say, I want to go this many meters per second, this many kilometers an hour, right? I want to accelerate, decelerate. If there's a person crossing the street, the planning stack needs to say, hey, I want to slam on the brakes, right? So at every point, there needs to be a speed profile. Speed profile just means speed along the path. So that's what makes up a full trajectory. It's path and speed and acceleration and jerk and steering wheel angle and lateral acceleration and stuff like that.
What's the resolution of this trajectory?
Varies, but generally pretty high resolution. It could be in time. It's usually in time. It could be in space. So it could be something like 10 centimeters between each point. It could be in space, in time as well. It could be 0.1 seconds between each point. Both work. I've seen both work really well.
How far in the future?
I've seen 2 seconds. I've seen 10. It's sort of, that's the range. It's sort of not too far into the future, not more than 10 seconds, because the world is very uncertain. Sorry, that far into the future. Not less than 2, because anything can happen in 2 seconds. You need to be ready. Hiba?
What about the blind spot, the car that's coming in the faster lane and how the car is accelerating in the faster lane?
Very good question. The planning stack needs to consider that. The planning system needs to know, hey, when I'm here, this guy can't see me. The planning system needs to know that. It needs to consider that. It needs to act safely with respect to that.
There's 2 things that can happen. When you're overtaking him, you don't want him to
Yeah, to come into you, exactly.
to the left in front of you
Yeah.
or next to you, but then also the car behind you don't want to bump
Exactly,
So
exactly.
it's two variables.
You need to consider all of them. You need to consider all of them. And the motion planning algorithms we're going to talk about are going to sort of talk a little bit more about how that's done.
Mahmoud, is it like most of the accidents like happen because of the planning, they don't have this scenario, or because of the other car make a mistake?
All of the above. Accidents happen within the world of autonomous vehicles because of everything. Really, it's a combination every time. So the other car can do something stupid. The planning stack could have put the car in a position where this car doing something stupid causes an issue. That's really not something we want to do, right? So sometimes it happens where it's really not your fault at all. That's rare. There tends to be things that you did wrong to put yourself in a position where you got hit or you hit someone. The famous Uber crash, that was part of it, was the planning stack sort of mismanaging its position. The cruise crash, famously, that was the planning stack sort of deciding to move when it lost sight of perception, right? So the planning stack is sort of oftentimes, due to its very high complexity, one of the areas where things can go wrong.
Is the car forward simulating each possibility at these points that it's putting? So
Good
if I'm
question.
at 4 seconds in, right?
Yeah.
Then I've predicted that that car is going to be here, and then what am I doing there, etc. Right?
Very possible. Different planning algorithms will do this differently, but yes, because we have a forward prediction coming from upstream, we sort of know, hey, 4 seconds later, exactly, this car is going to be in that position. The car behind me is going to be in that position. If I make this plan, I'm going to be in this position. Is that going to cause a collision? Is that going to be an issue? Is it an avoidable collision? Sometimes you have to plan for these unavoidable collisions and you sort of depend on people behind you paying attention. That's part of driving. So sort of in order to come up with this plan, the sort of high level critical considerations are on a high level, it's these. So you have safety. That's always number one, the most important, highest priority. You want to avoid a collision at any cost. You really don't want to cause a collision. That's the most important thing, right? You don't want to be the reason for a collision. Even higher priorities, you don't want to hit a pedestrian or what we call vulnerable road users, right? Pedestrians, cyclists, motorcycles, because hitting those is going to be very damaging. You don't want to hit the edge of the road. You don't want to fall off a ditch. Safety is always the number one priority. Smoothness, oftentimes, especially with older systems, you would notice that these self-driving cars, they will be very jerky. They'll slam on the brakes too much. If you have like a 2021 Corolla like I do, it reacts very late to obstacles in front of it. It basically slams on the brakes. Smoothness is very difficult. So a really good driver will always maintain safety while also having a smooth trajectory. If you've ever been in a Waymos are really good at this. This is one of the areas Waymos are very impressive and even better than Tesla in my opinion. They have extremely smooth trajectories. Efficiency, you're trying to sort of minimize everything sort of from like how long it takes you to get to your destination. Talking about Waymos being good at smoothness, they're really bad at this. Historically, until recently, I believe, Waymos didn't even drive on highways. So they maintained smoothness by going slow, but they went really slow, so they would arrive late. Tesla is better at this, right? Energy consumption for a car like Tesla, very important. Unnecessary stops, even at a routing level. You sort of want to maintain an efficient plan, an efficient route. You want to get to your destination, accomplish your goal. Feasibility is an important one that sort of, it's not something you would think about, but the motion planning system needs to put out a path that is physically doable. And that's not something that will come by default. Not every motion planning algorithm will necessarily by default have this as an output. So it's something we need to be very careful about, where if you have a car doing this, you can't have the next point in time be here, right? The cars can't move like this. We'll talk a little bit about this more in future slides.
Unnecessary stop sign.
It's more like on a routing level, you don't want to like route like through like a lot of stop signs when you can just go on a highway, stuff like that, right?
Could this also be humans taking advantage of the time of people being cautious?
Exactly. So you actually do want a little bit of aggressiveness, right? Without sacrificing safety and smoothness. It's a very difficult sort of engineering trade-off. So types of planning problems broadly split into two. Global planning, this is sort of the older, more solved problem. This is something you need to do on most systems. It's like just the routing, right? This is a picture of Google Maps, right? So this is, I'm here, I want to go there. Which roads do I take? Down to which lanes I take as well. So if you open up Google Maps, it'll tell you like, oh, you need to be on the right lane, or you need to like lane change to the right lane eventually, right? So this is a system that exists. It's a much simpler system. It's a very low frequency. It's like usually updated every few seconds, maybe every few minutes as you're driving. It's not trivial. Google Maps is good at it, not because Google Maps is solving an easy problem, but because Google Maps is just really good. But it is a system that cars need to do. This is a system that you can buy as well, right? A lot of companies would buy this from maybe even Google, right? Apple or something. You would buy the routing sort of module. You would buy the maps. Here, Maps is a famous company, TomTom Maps. They'll sell you sort of the map and the routing stack with it. And it'll have the lanes sort of laid out. Local planning, this is motion planning, right? So this is the topic of the talk. We're almost out of time. We're now sort of digging into this. It updates very frequently. It's 10 to 20 hertz again, as low as 5, but ideally 10 to 20 is sort of the range you want to be in. This is the idea of like, which exact path am I gonna go in? I'll go quicker. Yeah, real world planning scenarios. So these are some of the challenges you'll have to face. Really, you can think if you're self-driving and sort of imagine what things are difficult. Merging on a highway, very difficult. Unprotected left turns, very difficult. Lane changes and heavy traffic, very difficult. Your planning algorithm really needs to be able to handle all of these for whatever ODD you enable it in. I should have defined ODD earlier. It's just the domain that you allow the car to drive in, right? So highway is an ODD. Urban, sort of downtown is an ODD. The suburbs are an ODD. Construction is a very difficult ODD. Very difficult. Why motion planning is hard. So this is why my job is hard. Uncertainty everywhere. So we've talked about this a little bit. You have the idea of prediction error absolutely everywhere in your system. Your sensors are wrong. Your cameras are wrong. Your sort of upstream perception stack is wrong. Everything is wrong to a certain extent. By the time you get to motion planning, the errors have really accumulated, and sort of the uncertainty has blown up, and it's really difficult to sort of handle this level of uncertainty in the future of your environment, and even in currently what exists right now around you. Because like mirrors, for example, that's a source of error, that's a source of uncertainty. High dimensional state space. You're planning in X and Y in your sort of two-dimensional grid, but you're also planning acceleration, velocity. You're also planning the orientation of the car, the heading. All of those add up to sort of the dimensionality of your space that you're planning in. So you're planning in X and Y, that's a 2D space, but you're also planning in heading, you're also planning in velocity, you're also planning in acceleration. It's more of a 5-6 dimensional space. Real-time constraints, again, this 5 to 10 to 20 hertz, you gotta go quick. You gotta sort of be able to do all of this heavy calculation very quickly. And on modern sort of cars, the computers are actually not that huge. So Tesla is running an NVIDIA Orin, which, do we have one here? No, we don't have an Orin. I think we have an Orin Nano, yeah. So it's running a bigger version of the Orin Nano that we have in the back somewhere there. Not a very powerful computer. Oh, there's a Jetson Nano. I think it's the same stack under the hood. I think the Orin is a Jetson Orin Nano, yeah. So it's like this. How much was this? Not that expensive. Yeah, so the real Orins are, I think, a little bit more expensive than that, but not by much. Yeah, so it's a small computer. It's not a very powerful computer that needs to run all this computation fast. But
Sensors work in fog?
yes, cameras not so much. Cameras struggle a lot in fog, and this is sort of one of the main sort of reasons companies like to diversify their sensor suite, because the failure modality of one sensor. So famously, Tesla got rid of radar on a couple of generations. They had to bring it back because when cameras fail, every system fails in a certain condition. Cameras fail in fog, for example. That's a very good example of a failure case for cameras. You need backups. You can fail the system, but if like it gets foggy all of a sudden and you're a level 4 system, you need to do something. You need to get to the side of the road, right? You need to be able to handle that situation, right? So Tesla brought back radar. Waymo keeps LiDAR, even though they have a really good state-of-the-art camera system that's maybe better than anyone else in the world, but they keep their LiDARs because when cameras fail in fog, LiDAR has no problem, radar has no problem. When LiDAR fails because of retroreflectors, cameras don't have a problem. When radar fails because of metallic vehicles with sort of highly reflective straight surfaces like a Cybertruck or something, the sort of camera system doesn't have a problem, right? So they sort of complement each other.
How common is having two different planning systems for different situations?
Two different planning
So
systems?
nominal driving versus like, oh, we're in trouble, our camera has gone down.
Very common. Very common as a safety backup. So as every company I've worked in has something like this, right? So this is like a nominal system, and then when things go bad, you have a much simpler system that just tries to get the car to the side of the road to a safe location to stop, right? Until the problem goes away or until someone comes in to tow it or service it. And then yeah, competing objectives, all of these sort of things that we discussed in the previous slide about safety, comfort, efficiency, we've already sort of talked about how they're competing with each other, right? You can be more efficient and then sacrifice safety. You don't want to do that, right? So you have some sort of engineering trade-offs that you need to make.
Bring back redundancy, you pointed out.
Where?
You said brakes and redundancy.
Competing. Brakes and redundancy.
Put the word redundancy in the competing objectives, if it's relevant.
No. Redundancy is not a competing objective. That's more of how you achieve safety, right? So redundancy is the idea that like you have two computers. If one of them fails, the other one works, right? So it's not really a competing objective.
Is that what you alluded to for different sensor suites?
Different sensor suites as well, same idea, right? The sensors are redundant with each other. Even having two cameras facing somewhat similar directions, right? A lot of cars will have this. They'll have a camera facing front right and a camera facing front left. In the middle, you actually have two cameras basically covering the area. So yeah, redundancy, very important for safety.
Is it the cost is from the hardware itself?
That's a
or from
big
the
cost.
software?
Both are very expensive. The hardware gets expensive, depends on what kind of system you're talking about. A Waymo car, I used to hear estimates that a single Waymo car cost $500,000. I know that's been brought down a lot now. I think it's closer to $250,000 now. But even then, that's a very expensive physical set of sensors, right? And even they have like a big server rack at the back of the car. Computers, right? Those are sort of expensive. The software itself, very expensive, extremely expensive. Waymo burns billions of dollars every year. Every company burns on the order of hundreds of millions at least, just paying researchers to sort of come up with these motion planning algorithms and sort of.
So there's no open source, right?
There is no open source. Other than Comma AI, Apollo, the Chinese company, has an open source stack. Very few. And those are sort of very basic. They're far behind. No, this is all very proprietary. Back in Uber ATG, we had training. We had instructions that every couple of weeks they'd come in and tell us, hey, be careful. When you're in the bus, just commuting to work, don't talk about your work because someone might listen to you and hear what you're saying, and then they'll steal your ideas. And then you'll get in trouble for that. Like, it was that level of confidentiality.
So are they predicting a lot of profit when they figure this out? Like, why are they trying what happens if they don't do this? Like, people will still drive.
Yeah, so depends on level 2 or level 4, right? So for level 4 companies, especially back in the hype days in 2018, 2019, 2020, the sort of promise was, and this is what Elon Musk was sort of going around sort of saying, is that no one will drive a car ever anymore. Driving will be illegal. There's a famous CGP Grey video, if you guys are familiar with it. Humans need not apply. It's a great video. Very old, 10 years ago, I think.
Share it, please, everyone.
Yeah, I will share it. It's a great video. This is sort of the idea that everything will be automated. That didn't turn out to be true, but the investors at the time were like, okay, if no one's driving, then someone has to sell cars, right? So the cars that people will be able to use, buy or sort of use as Uber and taxis, they'll have to come from these companies, so they didn't want to be left out, right? It's somewhat still like true. I think just the timeline has been pushed by 10, 20 years, right? I think 20 years from now, I think most cars on the road will definitely be autonomous. You're already seeing this in California, where Waymos are sort of everywhere. In Austin, Texas, Zoox is another company that's sort of making good progress there.
So this is like the smartphone car. So if you don't do it, you're a BlackBerry.
Yes, exactly. I think that's what the word on the street is. Another sort of more modern race that's been very, very hot, like it's been picking up heat a lot, is the level 2 race, where people, consumers, have been more and more asking for autonomous features in cars. That's been driving sales, especially in emerging markets. In China, people really care about the car that drives itself better and better. That Mercedes car that sort of takes liability from you. A lot of companies are predicting that that's going to be a main selling feature for cars. So a lot of companies, Toyota included, where I work, are of the opinion that the self-driving feature of a car, the adaptive cruise control, is going to be a very important consideration for people buying new cars. So that's another area why. It's the whole system. It's the whole system is going to be very important, and they're willing to invest in that. How are we doing on time? Terrible. Path. Again, I like this picture a lot. This is a path, right? There's a path in a garden. That's what a path is. A path is in two-dimensional space, just a set of points, right? So this is, let's say, the 0, 0, 1, 0, and so on. So in two-dimensional space, this path defines how you're going to go through this garden. This doesn't have any speed or acceleration or something. It's just physically how you're going to go through the garden, right? Or the park, right? So this is a path. That's sort of an important word to consider. Trajectory is the concept of acceleration, velocity just attached to every point along the path. So in the future, how fast am I going to go? So you've all seen back in high school this really old picture of like, I throw a ball in the air, the y is like the height of the thing, the x is, I guess it's like location, and at every point we know it's velocity, right? So velocity at the end is going to be, or velocity of x at the end is going to be the same as velocity of x at the beginning, and velocity of y at the end is going to be the negative velocity of y at the beginning. Yeah, it's just the whole parabola thing. So this is a trajectory, right? So it's the physical path, and at every point we're sort of talking about what the velocity is going to be. We can also add acceleration to that. Jerk, and sort of you can go up that. Oh boy, we really need to go quick. Kinematic constraints. Kinematic constraints is the idea that when you have a car, the car can't do this, right? The car can't accelerate at 100 miles an hour or 100 meters per second squared, right? It has a certain limitation on what the car can do. Your motion planning stack really needs to consider that. It has a certain turning radius, right? Smaller cars will be able to turn much tighter turns, bigger cars not so much. A limo would barely be able to turn. That needs to be part of your consideration in your motion planning stack. The word bicycle model is a word you will hear very frequently. The idea of a bicycle model is that you actually don't need to consider that your car has 4 wheels. If you're familiar with differential steering, it's because when the car turns the wheels, it'll turn the 2 wheels separately, and you can draw sort of a virtual wheel in the middle. That virtual wheel in the middle tells you everything you need to know about the future position of the car. So we don't model our cars as 4 wheels in the motion planning system. We always model them as 2, exactly like a bicycle, right? Without the leaning of the bicycle, obviously, just sort of where the bicycle will go if you turn its wheels, its front wheel. Any questions?
This is an open area of math research where the back wheel doesn't do anything and the front wheel could be perpendicular or not perpendicular.
Yes. So that's a bicycle model.
What do I need to know about the front wheel?
You need to know its orientation with respect to the rest of the bicycle. Yeah, exactly. Or negative 90 to positive 90. Or whatever. So you also do need to know how far the wheels turn. It's not going to be negative 90. It's going to be a little bit less than that, right? It's going to be maybe minus 30 to positive 30, right? So you do need to consider that as well. All right, dynamic constraints, acceleration. I'm gonna skip this slide. We've pretty much talked about this. You can't accelerate infinitely. You can't sort of slam on the brakes infinitely. If there's a person crossing in front of you and you slam on the brakes, you're not instantly gonna stop. You need to consider that. Finally, the meat in the last 8 minutes. Maybe we'll go like 10 minutes over. So, types of planning methods. So, classical search-based planning is sort of the default, high-level, original way things were done in the world of motion planning. This is how like the early Roombas used to do things. Before optimization, before machine learning, we used to do sort of this. I think the next slide is pretty good.
Yes.
We used to follow this like super high level Dijkstra's algorithm. We still do this for routing. So you saw the Google Maps picture that I had. Google Maps is running this routing system. Any motion planning algorithm will have a Dijkstra system running on the lanes. Back in the day, early robotics days, this is actually how you used to do planning in the real world for cars as well, even, or for simple robots. I'm not gonna go into Dijkstra's algorithm because we're running out of space. Highly recommend it. It's pretty cool. There's cool videos about it as well. It's the idea of sort of propagating like an estimate of how long it takes to get to each point, and by the end you sort of end up with like the fastest route.
Is it Javadi's name or?
Dijkstra? Dijkstra is a genius. I don't know where he's from though. He's European. He is, I want to say German or something.
Why do you chop off a piece?
Where?
Why is it not a square?
Oh, I don't know. It's just a picture I found. I think it's just a graph. The graph can be anything, right? We'll see more pictures of graphs. So in the last slide, this is also a graph, and it's very random. This is a little bit of a cleaner graph with a chopped off piece. Yeah, so this is a really cool example of like what it looks like with Dijkstra. This is actually not Dijkstra, this is A star. So you can improve Dijkstra. This is really all the slide is saying. Dijkstra is fast. You can make it a lot faster with A star, D star, D star light. I worked with Professor Anthony Stenz, who invented D star light back in Uber ATG. This is actually one of the core algorithms they used in the Carnegie Mellon University for their autonomous vehicle. It was exactly like Dijkstra, except you evolve the estimate from both sides. Yeah. Does anyone know what this car is? Has anyone seen this before? It's a Lexus, but it's owned by a company, a very famous company. No, it's not owned by Toyota. The specific Lexus is not owned by Toyota. What does this top remind you of? It's a mattress. That's a good, yes. Yes. No one has seen this before? This is not a giant LiDAR. There are LiDARs in it. I believe these are solid state LiDARs on top. There's also radars. There's also cameras. It's a whole sensor suite. This is actually, no one knows, huh? This is Apple's self-driving car. Yes.
No one's seen this.
No one has seen this. People have seen this. If you're in California, you would see it.
I've seen Chrysler minivans with this stuff.
It might be Apple as well.
Yeah.
So this is Apple's, they called it.
Right here. At the
Maybe.
Shell station at Michigan Avenue and Lots. It was an Apple vehicle. It was.
Oh, did it say Apple on it? Those might be the mapping cars.
Yeah,
Those are
it's mapping.
no, those are different. This is a self-driving car.
It was self-driving.
Yeah, so Apple has actually dropped their self-driving project. They don't do this anymore. They fired a lot of the people working on it. Most of them they didn't fire. They actually moved to AI. Apple Intelligence is what they call it. The system they used was actually a grid-based system. So they used Dijkstra, A star. The graph that they designed was actually this sort of discretization over their lane. By the way, I interviewed with Apple. Funniest interview. They didn't even admit that I was going to work on a self-driving car system, even though everyone in the industry knows, like, we know they have this car and self-driving cars and stuff like that at the time. They just pretended like Apple doesn't make self-driving cars throughout the interview, and the guy was asking me, imagine you had an autonomous system driving in lanes, acting as if it wasn't a car. But yeah, it was a secret project. I think it lasted a good 7-8 years.
Oh,
Yeah, it's a huge project. Hundreds of people, maybe thousands of people
were you
working
at
on
the
it.
tail end of the 7 years?
I never joined them. I just talked to them. They canceled it. I think last year, maybe 2 years ago.
Do
No.
you know why?
No, I don't know. I know they wanted to make a whole car, an electric car, but I don't know why they canceled it. I think it was just burning too much money.
Maybe the level 4 hype was coming.
Maybe the level 4 hype was going away. Maybe it just didn't reach the sort of quality that they wanted and expected out of like an Apple product. I think a lot of it is also they wanted as many AI researchers as they wanted, as they could possibly get. And where do you find AI researchers? It's really hard to hire them. Yeah, so they just looked at their own company and they're like, oh, we have like these dozens, hundreds of AI researchers in Apple doing something that I guess some CEO or some executive thought was useless. Why don't we just hire all of those into the Apple Intelligence side of the company?
How can you combine the control system if it's from different company than the original car?
Good question. So that's the whole CAN bus. I think, yeah, like the AutoZar maybe has some standards for that. There are standards that you can just plug in and sort of plug into the computer of the car and sort of work with it. You actually wouldn't plug in directly into the physical systems of the car. You would probably plug into a secondary control system. So you would have your own control system talking to the car's control system, talking like actually outputting the voltages. So it'll be sort of more of a
I think
two-step
it is better
process.
to have the control and the car from the same.
I think, yeah, that would probably be faster. That'll be more predictable. But for a company like Apple, I guess they wanted just to get a physical car working as soon as possible. This picture down here is like until very recently. I mean, this is how people did planning, right? So you have this grid-based planning. You map the world around you, and you plan through it using Dijkstra.
Why are you yellow and green?
Where?
Why are you both yellow and green?
Here?
Yeah, in all the pictures.
I don't know. 2D, 2.5D. I think they're just comparing two different algorithms or something. I don't know where this picture comes from. I just Googled grid planning. It's a very common sort of approach for planning. But yeah, I don't know. I don't know why. I'll just skip this.
Please, just let me take a look. I won't ask.
Okay, yeah, I guess I'll go super quick. Discrete space, continuous space is sort of two common ideas. With grid planning, you absolutely need discrete space. So you need to chop up your physical space into, like, this is point number 1, this is point number 2, point number 3, so that you can form a graph. So you need this chopping up of the world. This is one of the limitations that I think Apple ran into, and why I think they eventually went away from discrete space planning and grid-based planning, because they ran into this really wide open space. Whereas with continuous space, you sort of don't need that discretization.
So you're gonna be talking RRT is continuous space.
RRT is continuous space. This is one of the cool things about it.
Quick question: is it discrete and continuous different from like what in control system is like?
No, same idea. So in control systems, exactly.
Because all the computers are like discrete, like so.
Yes, no, you're right. It's a little bit different. So with control systems, you're discretizing over time.
Yeah.
That is not necessarily just the case here. Here we're talking about spatial discretization. But a lot of the same sort of challenges you would run into with control system discretization of like, how do I choose my discretization interval, right?
Yeah.
That is the same sort of challenge you would run into with space discretization. Limitations for discretization, this is why I think it's really hard to get a discrete system working. This is why continuous space is often the thing you end up with almost always. On a 2D grid, let's say we have 100 by 100 points, which is not very high resolution. That's already 10,000 cells to search. If you make it 3D, so if you want to consider the z height, or if you actually just want to consider velocity. Velocity is an extra dimension you're adding. So 100, which is a very low resolution, 100 by 100 by 100, that's 1,000,000 cells that you're searching over. If you want to add heading, that's 4 dimensions. At 100 grid size, That is a very small grid size, but now you're doing 100 times 100 times 100 times 100. You're looking at 100 million cells to search, 100 million cells to index, and 100 million cells to sort of plan over and consider. Very difficult, very difficult. Doable, Apple did it for a long time. I don't know if other companies are doing, I haven't heard of other companies doing discrete space planning.
Continuous simpler than this?
There is no grid. There is no concept of grid at all. So you just don't run into this blowing up of space. You just consider each object for what it is, where its position is, where its velocity is.
What is like what is the unit of 100 by?
How many cells you have? How many like points? So like if we go back like here, like this is one box. This is another location the robot can be in. This is another one.
I think it's like centimeter.
Could be centimeters. It could be just like each box is like 2 centimeters by 2 centimeters, right? Could be each box is 10 centimeters by 10 centimeters. That's a number you have to choose, the size of each box, right?
So the 100 give you like 1 meter? Or what is the-
If 1 centimeter accuracy, yeah, which is nothing, right? That's if it's 10 centimeters for each grid, maybe that's a little bit better. That gives you what, 10 meters, right? Still not much, right? So the 100 is a very unrealistically small number. You actually need a lot more than that.
Do they have something called field of view? Like how?
Yes. So here the grid is a box. It doesn't need to be a square. It can be not 100 by 100. It can be 10 by 50, right? So you can sort of improve, sort of change the space, exactly, have a field of view. So there are things you can do to improve, and that's what a company like Apple would do. But ultimately, you just end up running into this problem. Like you'll end up running into this blowing up of sort of space. Like at 100 million cells, even with the best filtering, you still run into this problem. It's hard to avoid. So another approach that solves this sort of problem, throw it into a machine learning model. So Sheikh Ibrahim, he covered a lot of sort of machine learning algorithms, primarily around LLMs. This is sort of the idea of you train your system to follow either a known path or to accomplish the driving task. We can talk, I think we have, yeah, let's go super quick. I'm sorry, I know I'm going a lot faster. The reason ML is good, you learn from data. A company like Tesla, they have millions of cars. They have cameras on all those cars. They're learning from every car around them. They're learning from every driver. It's a lot of data. You can drive like humans. That's part of the goal. You want to drive better than humans, but starting from a human sort of benchmark is pretty good. With more data, you sort of see more complex scenarios. You also don't need to do this discretization. You don't need to handle individual rules. End-to-end potential, sort of you can learn from your sensors directly. You can sort of avoid this like sensing, then perception, then prediction. Then like you can avoid having these separate blocks. You can have this end-to-end learning system with a machine learning stack. You can't do that with a traditional stack. And adaptation, you can sort of, with more training data, you can sort of be able to drive in different environments. You can fine-tune for specific. Sheikh Ibrahim had a whole lecture on fine-tuning, right? So you can also do fine-tuning with driving. You can fine-tune your models to drive on specific cities, specific kinds of environments, and you can have multiple models. 2 ways self-driving cars do this. One is reinforcement learning. Reinforcement learning. Anyone heard of reinforcement learning? Few people, mashallah. Reinforcement learning is the idea of you have an agent, a robot, that does an action in the environment, observes a reward, and then sort of learns based on how well its actions influence the rewards it sees, right? So the car will be in a simulation environment. It'll try to drive. It'll do something dumb. It'll hit something. The simulation will say, hey, you hit someone. Don't do what you just did. The model will go back and learn. I love reinforcement learning a lot. This is a book that is a very famous book, Satyanam Barto, that teaches sort of reinforcement learning. Reinforcement learning actually predates machine learning or predates neural networks. So this book actually, like 90% of it is not even about neural networks. You can go really far with the reinforcement learning, But, and I think the next slide, yeah, the next slide has some pros and cons. It's really hard to get working. It's really, really hard. I really don't think any companies have a pure reinforcement learning stack at all. Many researchers have that. If you go to a university, you'll have a lot of research papers that are just pure reinforcement learning for autonomous vehicles or for autonomous driving. It doesn't work that well because of these cons, so it requires a ton of training data. Training data comes from simulation in this case, but we're really talking about a lot of simulations, right? Google, Waymo, they do well with reinforcement learning. They had a really good papers with reinforcement learning because they have Google infrastructure, right? This was before LLMs where they needed to share their Google infrastructure with other more hyped things like Gemini. So they used to sort of have these massive simulation systems that would like train like over billions of hours or millions of hours, I think even billions, yes, of hours, and just keep iterating and learning from their behavior. Even then, it was really hard because it's really hard to, this is phrased weirdly. Exploration, you need to explore the world, right? There's two ways to do that, simulation and the real world. If you do it in the real world, can't do safety, right? You're exploring sort of possible outcomes, but if you choose to explore a dangerous environment, then you hit someone. That's bad in the real world. In simulation, the simulation stack is limited. You're limited to what you can simulate because someone needs to implement that simulator. There is a company in Toronto called Wabi that is trying to do this like automatic simulation of environments without having people physically create it. So they'll like use machine learning to create an environment, and then the car will explore that artificial environment. Still very difficult to get that right. Very computationally expensive. Reward engineering is tricky. So in the last slide, the little robot got a reward from every single action it committed. This is not a machine learning component usually, right? Except for the case of reinforcement learning. This is usually a thing that's designed by humans. So this is a thing that says like, hitting a person is bad. Okay, that's easy. But like accelerating too much is bad. Slamming on the brakes for no reason is bad. Having the car go out of its lane for no reason is bad. Forgetting to use your blinkers is bad. You sort of end up with a lot of things in this reward function. And now you have to tell the robot which one's more important. You have to do a trade-off. Yes, hitting a human is the worst thing you can do, but which one's worse? Is it worse to slam on the brakes, or is it worse to leave your lane? How much is each one worse? In which situation is each one worse? This is a human engineered component that is very difficult to get right. And this is where a lot of research ends up being. This is where a lot of companies run into trouble. This reward part tends to be the most secretive part of any reinforcement learning system in industry. It's very difficult. Sim to real transfer. Oh yeah, if you train in simulation, there's no guarantee that whatever happened in simulation is going to happen in the real world. Your simulator could be wrong. You could slam on the brakes and the car stops in 5 meters in the simulator. In the real world, there could be rain and the car stops in 10 meters. Now, whatever things you learn in the simulator will cause you to stop incorrectly and cause an accident in the real world. Your simulator is never going to be perfect. I know Zarek is going to try to make it perfect. He's a simulation engineer, but it's never going to be perfect. And so, sorry, Zarek, but it's always going to be limited to sort of things that don't match reality. And when you train on that, you end up learning incorrect things that can get you in trouble. Another approach.
Is it worth keeping though?
Yes. This is actually a good example of where RL is handy. You can sort of combine between sort of, I'm just going to go quickly through the slide because there's a lot here. You can combine between imitation learning and we'll go back to that slide actually. Let's do this one first. And reinforcement learning. Let's talk about imitation learning quickly. I'll go back to reinforcement learning. Imitation learning, this is what Tesla does. This is what a lot of companies do. This is what Waymo does. This is what we do. This is what almost every company does these days. You learn from examples. You just have your cameras. You detect how people drive. You learn from what they did, and you sort of copy it over thousands, hundreds of thousands, millions, billions of examples. The way you can get billions of examples is by saying, let's take a 10-second snippet of how this person drove just now. Now let's move forward by 2 seconds and take the next 10-second snippet. Now those are two different snippets that you're learning from. And sort of these companies spend a lot of money, and a lot of data centers that Faris is building, sort of getting this right, getting as much data as possible, and getting that training loop sort of to copy the human data. Ways this is done, behavior cloning is sort of this traditional state-of-the-art, most common way. Dagger is sort of behavior cloning with a little bit of feedback, and inverse reinforcement learning. I'm not going to go too much into inverse reinforcement learning. It's a whole world. The idea is that reward function I was talking to you about, you try to learn it from your data, but you maintain a sort of reinforcement learning loop. I don't think, as far as I know, inverse reinforcement learning is less popular these days. I know it used to be really popular. And yeah, so you can combine between reinforcement learning and imitation learning. I'll stop in 2 minutes. You can sort of combine between those two by first doing imitation learning, and then by sort of having this reinforcement learning part later to improve your system beyond your data, do better than humans, right? So you bootstrap with the human data, and then you do better. Oh man, we didn't even get to RRT. Maybe next time. Yeah, maybe we go to part 2 later, because it's getting late. I don't want to keep people longer than is necessary. Any questions? We'll do a part 2 maybe as a Thursday tech talk. How about that? Yeah, I think that would be good.
You want to do like hands-on?
We could do a hands-on. I do have a cool workshop here.
So is it better for like a Sunday then?
We'll talk about it. I don't know how much more time we need. Questions?
There's a coding exercise.
There was a coding exercise. It's getting
So
late.
maybe, like, have a camera on a small robot.
No, not that cool. I will show you since you guys are here. I guess we can stop the recording. I'll leave this so that people don't see the sneak peek.